Hello, my name is Dan. This is the second in a series of webinars on research methods and statistics in support of our university faculty initiative, strategic initiative to support faculty in their research. Today's topic is statistical significance and how they differ from measures of effect size. During webinar number 1, I had mentioned that our students often confuse statistical significance, the p-values, and effect size, and not to make that error. And so this came up as a request for the second webinar. Happy to do so. Let's make this a little formal. My name is Daniel Lowfold, PhD. I'm an associate professor and teach out of the EDD and DHSC program. We also want to make these webinars available to those folks who are potentially interested in joining us in the EDD and DHSC program, or for those folks who are interested in seeing about the other program offerings at USA. There's our 1-800 number, our website. You're always free to send me an email. Would love to have you join us. So let's chat a little bit about statistical significance. I have a hard time with the word statistical. We see them in summary ANOVA tables, such as you would find with ANOVA, or we would find the p-values associated in a one-sample t-test. So they show up both in table form and inside of the manuscript. What I find real interesting is that here we are in 2012, and there still remains persistent lack of understanding, for lack of a better term, about what it is that these p-values are. Some time ago, I was talking to an instructor who's he considered himself a good evidence-based instructor. But as we spent more time together, I come to find out that he didn't really understand what p-value was. So it does sort of beg the question, if it's our job to help students understand the literature out there, then I think it's incumbent upon us to make sure that we understand what these things are and what they are not. Emotions run pretty high out there in the world about statistical significance testing. There is one camp who would request that we completely exorcise them. Get the demons out. Exorcise them from our vocabulary, our language, and our very use. There's some articles that you can take a look at the fervor, the heat, and the fury about significance testing, but especially a particularly good article you're going to find by Larry Daniels, and it's called The History of Misuse, and I'm going to talk about some of those principles here. In graduate school, I was asked to give a presentation to a bunch of deans and our provost about significance testing, and I just said basically it's a misused idea. And at the end, the provost asked me, I was at University of Florida, the provost asked me, "So Dan, do you think we'll ever get rid of these?" And I just had to tell him, "Sir, no, we never will. They'll be with us forever." But what we can do is try to use them in an intelligent fashion, and so that's what I'm going to talk about today. So in webinar number 1, it says that students often make mistakes, and students will conclude if the p-value is real small, it's better than if like a p-value of 0.001. And well, then we know something more than if we just have a p-value of less than 0.05. That somehow having a small p-value is a good thing in and of itself. And here's a t-shirt from the Zazzle folks. Got a lot of nerd t-shirts out there, but this one tickles my interest. So this is what we're going to talk about, p-values. Probably the first thing we need to come to grips with is that the p-value, the value of statistical significance, is a function of how large our sample size is, what n is. I'd ask you kindly to look carefully at the tables that I present here, because it took me a long time to make them. I have SPSS, the full faculty version of it, and with it we are able to generate numbers, generate data sets that have certain characteristics. So what I would ask you to take a look at here is I've done two different, this is called bootstrapping. I've done two different sets of bootstraps. One with a control and treatment size with 20 subjects in the population, and another with 40. Notice that in both the N of 20 and the N of 40, that we're generating ostensibly the same means, and they have the same amount of noise in the variable. Okay? So same noise, same effect size, and then if you look at the table below, look what happens to see, I really have a tough time with that word, statistical significance. When we had 20 subjects in the group, our significance was at 0.137, but again, the same effect size, same noise. When we have 40 subjects, we have a p-value of 0.032. In this situation, with 40, we would reject the null hypothesis and conclude that our hypothesis is correct. Of course, if we just had 20, we would fail to reject and conclude that our experiment is not working out. So this seems to not make intuitive sense, right? So this relationship between p-value and the size of the sample population shows up not just between tests of the difference between means. Tests of the difference between means is a point estimator. Now, that other category of research that we do is research based upon correlation. So what you see here in the screen is different sorts of correlations. This is a simple Pearson R. And you can see correlations that run as high as 0.997 and as small as 0.0196. And if you are following along, I could tell you that each one of those R values can be statistically significant at the 0.05 level or better. As you can see here, the way that we make those statistically significant is we increase the sample size. So if we only have an N of 3, we can have statistical significance, but that correlation has to be as high as 0.997. Now, even a correlation as small as 0.019, and not only the interrelationship between two variables being less than 2%, is statistically significant if we have a population of 10,000. Right now, I'm working on a contract that I was obligated to do out of the state of Wisconsin, and I've had to I keep reminding the principals that when we run the data, all of our effects will be statistically significant because we got a population of 14,000. So any sort of differences are going to show up as statistically significant. In research methods and statistics, what we have too little of is applied common sense. This is coming from a guy that didn't necessarily have the highest math scores, so I have to figure out a way to make sense of things in a concrete way. Otherwise, I can't make sense of anything. So here we have Dr. House, and he's going to run an experiment. His control group is women, his treatment group is men, and he wants to know how women and men rate his relative arrogance level. It ranges from 0, not arrogant at all, to 150, arrogant beyond belief. So this is our little experiment. So I'm going to play the role of interrogator, and so I'm going to ask Dr. House, so Dr. House, you're asking if men and women come from the same distribution of beliefs about your arrogance, or if the distributions are in fact unique. In other words, that's the question that we're supposed to be asking. But for the most part, that's such a heady little proposition. Dr. House and other folks are likely to say, whatever, Lowfall, you know what I'm talking about. I know what they're talking about. I'm not entirely sure that they know what they're talking about. And that's the purpose of this webinar. So let's say that Dr. House, being a man of science, he asked Dr. Kuttner to go out there and get some answers for him. In other words, go poll men and women about his arrogance level. By the way, I'm really upset over them Xing Dr. Kuttner from that show. You might want to investigate why. It's very annoying. Anyway, so Dr. Kuttner, what did you discover? And he answers that women gave him an arrogance rating of 92.5, and their standard deviation was 6.5, and men gave you an arrogance rating of 9.6, and their deviation is about 6.5. So that's the evidence from Dr. Kuttner. And again, Dr. House, being a man of science, wants to replicate his project. So he asked Dr. Wilson to go out there and similarly collect data. And Dr. Wilson reports exactly the same means and standard deviations, same effect size, same noise for men and women as Dr. Kuttner. Kind of interesting. Dr. House might conclude that he has the answer to his research question, that women find him less arrogant than men. It must be his charm and blue eyes. Again, in my role as interrogator, I might ask him if there's anything he might be failing to ask his data collectors. Taking his cue, Dr. House might ask his two data collectors how many people they actually interviewed to get that data. And Dr. Kuttner asked 4 women and 4 men. Dr. Wilson, being the fastidious, more anal retentive type, asked 24 women and 24 men. Dr. House might at this point be a little bit confused. He says, my people came up with the same results, but obviously he's a little bit more confident in Dr. Wilson's conclusions. So kind of what is that? So this is where we're kind of getting to the essence of what a p-value is. It tells us how much confidence confidence is warranted in the samples that we're collecting in our data collection process. So in this instance, Wilson would have had a smaller of the 2 p-values. It would be really easy for me to come off as haughty and arrogant myself, talking about other people's mistakes in their interpretation of p-values. Hopefully I'm not doing that, because the truth of the matter is that it really is a difficult concept. I got a lot of sympathy for the wrong-headedness out there, because even the people, and principally this is the problem, the folks that are actually teaching the statistics are getting it wrong, if not horribly wrong. And to ultimately to put some sense to this requires a relatively robust and difficult mental construct to keep in mind. So I'd like to try to run it by you. Let's see if we can do this. So one of the things that people are first surprised to find out is that statistical significance testing, those p-values, has to do about sampling. It doesn't have to do with effect sizes. So let's do this by the numbers. Statistics is about taking measurements from samples and to make conclusions about populations. For example, imagine somebody having a research study where the sample consisted of 22 occupational therapists. That's a sample. But the intention of the study, when they get to the write-up, is that they want to generalize to occupational therapists as a whole. Well, Wikipedia tells me there's 104,500 of them. So we have the sample, the little n, and then the sample, the big N. So statistics is about gathering data from samples and making conclusions that are somewhat warranted about the nature of populations. So at the risk of repeating myself, statistics are a process for analyzing samples and to do it in a way that we can hopefully make warranted conclusions about populations. Statistics don't tell us what is, it tells us our approximation of what is. In this decision, we can be in error. So, many of you have seen this decision matrix before. On the top line, this is what is in reality, only knowable to some sort of omnipotent deity. Or if you actually had a sample of all 104,500 occupational therapists as our population. But generally, we don't have access to the population. We have access to the sample. And then we attempt to make decisions. As you know, we test the null hypotheses. We test that there is no difference between the two means. And in that, we can be correct in two ways and incorrect in two ways. If you look in box number 1, blue, if reality had it that there was no difference between the means and we failed to reject the null and keep it, we would be correct. Likewise, if in fact the two populations were different, if our experiment really did work, and we rejected that null, then we would also be correct. Of course, the two types of errors that we can make is type 2 error, and this is the one most common to all of social sciences and occupational therapy and physical therapy and the rest of the health sciences as well, and that is when in reality the experiment worked, but we conducted the experiment in such a weak fashion that we reduced the probability of finding an effect that was truly present. Type 1 errors are just due to bad ethics. Something we can talk about in a different time. There is a way for us to play the role of omnipotent being, and for me it would have to be a Monte Python omnipotent being. And that is to generate a huge data set. So again, with SPSS, I can generate random numbers that have very particular parameters. So I told SPSS to generate 500 numbers with a mean of approximately 100 and standard deviation of 15. Now, because they are, in fact, real random numbers, what I ended up getting was a mean of 99.64 and a standard deviation of 14.41. Okay, so from that, we can treat this as the treat this as the population, the big N, and then see what happens with a couple of samples. So we can do applied common sense. Okay, then playing the role of House, as you remember, since Wilson sampled more people, he felt more confident in Wilson's conclusions. Now, when we take a look at that population of 500, then again SPSS can randomly sample from that data set. And so what I've done is created 5 samples each of a sample size of 5, 10, 35, and 70. What I'd like you to attend to is the fact that when the sample sizes are small, both of the means are not all that great of estimators. They can be quite wonky. But as we go from very small sample size to larger sample size, the numbers themselves more approximate the real population values. So, as I mentioned, all statistics are chance adjusted. And so this is why when we have a larger sample size, we have more confidence that it's a good estimator, and the p-value for any given effect gets smaller. So if you see how wonky a sample can be with 5, imagine how wonky a sample can be where you're dealing with a single subject. Personally, I don't get case studies at all. So once again, you can see it on this screen as well. The calculus that undergirds statistics does chance adjustment, and we see it here in the effect size and what happens to the relative p-values. So let's do a little bit of practice. There's more than just the 2 ways that I'm going to show here to talk about what is statistical significance, but I'm going to get you close on these 2. So if we assume that the control and the treatment groups were sampled from the same theoretical population, so we start out with that assumption, we're asking the question in doing these statistics, what is the relative probability of finding 2 means that differ by 3.16, the difference between those 2 means, with approximately 6.5 units of noise or variability in the distribution? So that's the question that we're asking inside the statistic. And as far as an answer would go, it depends. The probability of finding a difference that larger, strictly due to chance, is about 13.7% if we're pulling from a sample of 40. However, that same effect size, in that same amount of noise, the probability of finding an effect that large or larger is now reduced to 3.2%. Why? Well, because means and estimates stabilize, and we've seen that in a previous screen. There's another way to describe statistical significance, and that is, the calculus, by the way, is exactly the same, is if we were to replicate the study with exactly the same subjects and exactly the same procedures, what is the probability of us finding an effect size that large? Again, it depends upon the size of the sample. With a larger sample, our chances of finding a wonky difference between 2 means by due to chance is reduced. So there's another way of thinking about significance. So, in summary, statistical significance and the p-values inform us about the probabilities associated with sampling. That's generally hard for students to come to grips with on the front end. Statistics adjust for the confidence that we should have in them, given the size and the properties of the samples that are in our study. And all high quality quantitative methods allow us to quantify and estimate our ignorance. We'll talk about that in a future webinar. So, what makes p-values particularly silly is that they can be misused. Somebody doing a study, and if they want to make sure that their experiment works out and the p-values fall below 0.05, all they have to do is increase the sample size. So at that level, they're a little bit silly. So p-values by themselves are not enough. It's our obligation, if we're going to be evidence-based instructors, it's our obligation to make sure that students understand how to not overinterpret p-values. And what they need to do is to add to this knowledge, learning how to interpret effect sizes. Okay, here's a chance for faculty to test themselves. So here I have 3 different sets of controls and treatments, 3 different experiments. And what I'd like you to do is take a look at this and tell me which one of these 3 experiments, A, B, or C, produced the most impressive results. Hopefully many, if not most of you, understood that the problem with different scaled measurements, as we can often find in the difference between means, is we need to know what the normalized effect is. And so here's where we divide the differences between the means by a pooled standard deviation. And when we did that, we find out that experiment C had better results. And of course, the big dog in effect sizes was Jacob Cohn. You can get his original article right there. The information that you see in the red bracket is the Cohn's D, or normalized value. And Jacob Cohn suggested that effect sizes around 0.20, he would consider those small, and large would be an effect size of 0.80. I think we need to hang a question mark on that, and I'll speak to that a little bit more. So we can use Cohn's D when we're talking about experiments where we have the differences between means. And of course, we also have all those experiments that have as their basis correlations. And so he reports out in this little chart here R values, 0.1, 0.3, 0.5. But hopefully you remember that if we want to understand how much variability in the dependent measure can be explained by knowledge of the independent measure, then we need to take these R's and square them. So an R of 0.3 becomes 0.3 times 0.3, or approximately 9%. We have 9% shared variability. And like what Cohn's claiming here as a large effect size being 0.50, well, we have to square that. And then he's suggesting that if we have 25% of shared variance, he would consider that a large effect. Also, we have different sort of correlations and other different sort of effect sizes associated with them. So you've probably seen them before. It would be things like eta squared, partial eta squared, omega squared for fixed factor models, something we talk about in a future webinar, and of course interclass correlation coefficients, like many of the occupational and physical therapists do, inter-rater reliabilities. So there's effect sizes associated with those that are slightly different than R squared, but they're ultimately interpreted the same. And of course we have another category of statistics, binary logistic regression, ordinal regression, and they produce effect sizes that are odds ratios. It's a heady topic. We can talk about that some other time. Now, my take on Jacob Cohn is he was a real smart guy up until the point that he published that chart where he told the rest of us what was considered small, big, and large. At that point, he lost his darn mind. So I loathe this chart, and I loathe things, any cookbook prescriptions of a similar ilk. Now, the reason that I do not like Cohn's prescription is because what ends up happening is people quit thinking. Students will report to me that that this was a moderate effect size according to Cohn. And I'm saying, who's Cohn to say? You're the physical therapist. Is an effect that big meaningful, or is it ultimately just decimal dust? In other words, we always have to make the distinction between statistical significance and practical and clinical significance. So when we use charts of this type and kind, we really do ourselves a disservice. Let me give you an example, what I would consider applied common sense. I have a student right now, bright lady Elizabeth, and she is hoping to find a correlation between teacher classroom questioning techniques and what ends up showing up as different measures of epistemological sophistication used in a very well done and well validated instrument. So Beth has to be able to capture some pretty significant variance here. She needs to capture at least 25% before we consider her project to be useful. Okay? Take that in contrast with work that's done in achievement motivation. This research line has about 35 years of active work on it. It's been worked on by more than 50 PhDs and at least $150 million worth of research. This theory is so blasted powerful, it'll blow your mind. Now, Carol Dweck, the principal investigator here. Let's say that she comes up with a refinement of her project and now all of a sudden captures 6% more variance with her new idea, maybe a factor analytical solution or something like that. It's going to make the Chronicle of Higher Ed because she has otherwise squeezed so much out of this, and the idea of her capturing just a little bit more would be entirely newsworthy. So we have to be thinking about these effect sizes relative to the context in which these experiments are going on. So let me close this out here. I think our obligation to our students is to help them become aware that statistical significance testing can be a lot of fairy dust. And we're obligated not to overinterpret those. And if we're going to use the p-values, they certainly must be used in conjunction with a critical look at effect size. I observe Cohn's definition of what is medium, large, and what we need here is more thoughtfulness in terms of what the research is reporting. So thanks for joining me. I hope you have a good day. And again, if folks have suggestions for the next webinar, just let me know. All right, peace.